Hello everyone, I'm Paul and today we're solving problem 1590. Make sum divisible by p. This is medium and interesting, so let's start. We are given an array of positive integers nums. So let's say that this is nums and we need to remove the smallest subarray, possibly empty, such that the sum of the remaining elements is divisible by p. We are also given p, here p is 6. It's not allowed to remove the whole array, so if the smallest subarray has a size of n, meaning it includes every element, we need to return -1. So if we had an array with only this, the sum of this array is 3 and this modulo p is 3. Given that this is not 0, this is not divisible by 6. And the only way to make this divisible by 6 is to remove this element. So if we remove this, now the array is empty. And given that we are not allowed to remove the entire array, we return -1 in this case. If this is nums, the sum here is 10, and this modulo p is 4. Given that this modulo 6 is different from 0, this is not divisible by 6. So we need to remove one subarray. In case you know what a subarray is, it's a contiguous block of elements. So this is a subarray, this is a subarray, but we can't form a subarray with 1 and 2, for example, because these two elements are not contiguous. So now the question is, which subarrays can we remove? How do they look like? Well, if we remove this subarray, now the sum of the remaining elements is 6, and this modulo p is 0, meaning this is divisible by 6, so we could remove this, and the result would be 2. The thing is that we need to find the smallest subarray. If we take this subarray instead, now the sum of the remaining elements is also 6, and this modulo p is also 0, so this is a valid subarray, and this is smaller than the previous subarray, so the result is 1. So for this input we return this. Now let's see what's happening here. This is a valid subarray, and if we take the sum, 3 plus 1 is 4, modulo 6, 6 is 4p, the result is 4. And if we take this other valid subarray, here the sum is also 4, modulo p, result is 4. So it looks like we are looking for some subarray with a remainder equal to the remainder for the entire array. And this is the main observation for this problem. We can take the total sum of the array modulo p, and we are looking for a subarray with this remainder. We are looking for the smallest possible subarray with this same remainder. Now maybe you are thinking about trying every possible subarray and keeping the smallest one with this remainder, but the problem is down here in the constraints. This will require big O of n squared times complexity, and here n can be up to 10 to the power 5, so this is a very big number. We need to think about something else. And for this, you should be familiar with something called prefix sum. Let's see how this works. Let's say that we are trying to get the sum of these two elements efficiently in big O of 1 times complexity. How can we do this? Well, we can build a prefix sum array, and here we are storing the sum up to every index. First we have a 3, so the first value here is 3. Then we take the current element plus the accumulated sum, 3 plus 1 is 4. Then we take the current element plus accumulated, this is 8. And then we do 8 plus 2, this is 10. So if we're trying to get the sum of this array, we can take the right bound, meaning 10, and subtract the left bound -1. 10 minus 4 is 6. And 6 is the sum of these two elements. And just to be clear, if this is the original array and we are trying to get the sum of these two elements, we can take the prefix sum up to the right bound, meaning we take the sum of all of this and subtract the sum up to the left bound minus 1, meaning we subtract all of this. That's how we get this range, which is exactly what we want. Now, this is slightly different because we are not only trying to get the sum of different subarrays efficiently. We need to get the sum modulo p efficiently. So we can do something very similar. We start with 3, and here we put 3 modulo p. This is 3. Next, we can continue with the accumulated value plus the current value. 3 plus 1 is 4. Modulo p, the result is 4. Then we do accumulated plus current, 8 modulo p. This is 2. So here we put 2. Next, we take the accumulated value plus the current value, 4 modulo p. This is 4. And that's it. So now, if we want to take the sum of this subarray modulo p, we take the right bound, 4 minus the left bound minus 1. 4 minus 4 is 0. And we do this modulo p, meaning 6. 0 modulo 6 is 0. And this 0 corresponds to the sum of the elements in this array. 4 plus 2 is 6, modulo 6. Now let's say that we're trying to get the sum of this subarray modulo p. We can take the right bound, 2, minus the left bound minus 1, 4, and this modulo 6. This is minus 2 modulo 6, meaning 4. And this 4 corresponds to 4 modulo 6, so this is correct. And this is how we can implement prefix sum with sum reminder. And this is very important because we can do lookups in big O of 1 time complexity, which is very efficient. Just to be clear, here we are taking the right bound minus the left bound minus 1, we will call this L, modulo p. Now going back to a problem, remember that if this is equal to the target, we can remove this subarray. Here the target was 10 modulo 6, meaning 4. So we could remove this subarray because this is equal to the target. And the final question here is, how can we solve this in big O of n time complexity with this information? Instead of having this array, we are building the prefix sum with an integer. We start from 0. And we will call this variable prefix right. This is the prefix sum for the right bound of the formula. This is the accumulated prefix sum at every point. So we are iterating this from left to right from index 0. Here is the I pointer. This is initially 0. We are here and we do 3 plus 0 modulo p. And the result is 3, meaning the accumulated prefix modulo p up to this point is 3. Now we know that the target for all of this is 10 modulo p, meaning 4. Now the question is, if this is prefix right, meaning the prefix sum modulo p for this subarray, where is the left bound? Given that we have this, this, and this, we can solve for left. So if we solve for left, left is right minus target modulo p. And this is the ideal left given this target, this right, and this p. So what is left here? We take right minus target for modulo p. And this is minus 1 modulo 6, meaning 5. Now we are checking if we have already seen this left bound. This is the ideal left bound for this target. So if we have already seen this, this means that we found a valid subarray. How can we check if we have already seen this? Well, we can have a map. Here keys are prefix sums modulo p that we have already seen, and values are indices. And initially we have a key of 0 equals to minus 1. This is because if left is 0, this means that we want to take the entire subarray from the start of this array. So given that we don't have a 5 here, we don't do anything here and just add prefix right to the map. Given that we don't have a 3 here, we add 3, and the value for this is the current index, meaning 0. And now I think it will make sense. We are here at index 1. We take the current number plus prefix right, and this is 4 modulo p. The result is 4. So now we are looking for the optimal left bound. We take right, meaning 4, minus the target modulo p. The result here is 0. So we are checking in our map if we have a 0 and we have it right here. This means that this subarray is valid. At this point we can add to the result the minimum between the total amount of elements, meaning 4, and the size for the current subarray, meaning 2. So we put 2 here. And now we have already seen this prefix sum modulo p, so we need to add this to the map. We go here and we don't have a 4, so we add 4, and the value is the current index, 1. Now the I-pointer is here, so 4 plus 4 modulo 6 is 8 modulo 6, meaning 2. So we need to get the optimal left bound given this right bound, this target, this p. So left is right minus target modulo p. And minus 2 modulo 6 is 4. So now we go to our map and we check if we have already seen this prefix sum modulo p. And we have it right here at index 1. So now we can take the current index 2 minus this index 1, and this is 1. This means that this is a valid subarray. And given that this is smaller than the current result and we are trying to get the smallest subarray, we replace this with 1. And now we need to add the prefix sum modulo p that we have already seen at this point to the map. So we add 2 as a key, and the value for this is the current index, meaning 2. Now we are here, so we take the current prefix right plus the current number modulo p, and this is 4. So now we need to get the optimal left bound. We take right minus target modulo p, and this is 0. Now we go to the map and check if we have 0. And we have it right here at minus 1, meaning this entire subarray is valid. Actually, it's not allowed to remove the whole array, but in terms of the main logic, it is valid. So now we keep in the result the minimum between 1 and the size of this 4. So we keep 1 here. And we need to add this information to the map. So we go to the map at 4 here, and we update this with the current index. This is index 3. And maybe you are wondering why. Why are we doing this? Well, if we are iterating this from left to right, and we want to get the smallest subarray, we need to update every prefix modulo p with the new index. By doing this, we make sure that we always get the smallest possible subarray for this prefix sum modulo p. So now we update the I-pointer, reach the end, and return 1. And by doing this, now we are solving the problem in big O of n time and space complexity. So with all of this in mind, now let's go with the code and hopefully you will get the idea. First, n is the length of nums. We have a target, which is the sum of nums modulo p, and here we can say if this target is 0, we return 0 right away. Why? Well, because we don't have to remove anything here. Now, the right bound for our prefix sum modulo p is initially 0. We will call this PR, and we are storing prefix sums modulo p that we have already seen in a map. We are calling this map scene, and this includes initially the key value pair 0, minus 1. The result is initially n because this is the maximum size of any subarray, and finally we want to return result if result is different from n, else minus 1. Why? Well, because if we have to remove every element in the array, given that we are not allowed to remove the whole array, we return minus 1. Now, for every index in range n, every time prefix right is prefix right plus the current number modulo p. And now remember how we get prefix sum modulo p efficiently. We take sum right bound, we are calling this PR, we subtract sum left bound, and this modulo p is the value for some subarray. Now, the ideal subarray here is the one for which this is equal to the target. So if we solve for PL now, we get PR minus target modulo P. And now we can check if we have already seen this left bound. So if PL in seen, result is the minimum between the result and the current index minus the corresponding value for the left bound, which corresponds to the previous index. So this is seen PL. And now we need to add to seen the corresponding index for the current PR. This is the current index. And finally we return this. So this is the entire code. Now let's submit this. As you can see, this works and it's very efficient. So if you found this useful, please drop a like, subscribe, and see you in the next one. Bye bye.